After last year's presentation, we received loads of great feedback. It seems many in our audience were craving more PowerPoint slides. So this year, we have 72 slides in the main deck and another 47 in the backup deck. I'm John Wolfe with Mullarney Technical, and I really hope you enjoy this year's edition of Death by PowerPoint.
I'm Alasdar Mullarney, also of Mullarney Technical. We're presenting on our latest challenging project, on which I'm enjoying working with John again, whom I've known since the last century. Yes, we're that old, grey hair or not, as the case may be.
Our customer is developing a platform and a tool chain for software-defined vehicles. Think Android with wheels. Armed with a vehicle guidance model described during previous editions of this conference, our clients are building tools to evaluate the behavior of vehicles, both automated and manually driven. They do this by stimulating these models with data pulled from vehicle logs, and then they compare that behavior to the behavior specified by the vehicle guidance models. The vehicle guidance models are developed in scrawl and flatland because, well, pushing pixels is really hard work.
I've been pushing pixels my entire career and I am done.
So that's where the name comes from. At present, our clients manually transform these models from flatland and scrawl into Mika, a language designed for expressing a platform-specific model. The Mika toolchain then translates these Mika expressions into C, and that C is compiled into an executable program. This approach requires an instance population of the road subsystem of the vehicle guidance domain corresponding to the actual driving environment in which the vehicle log was recorded. This instance population is then incorporated into an executable representing the vehicle guidance domain, and that executable is used to evaluate vehicle behavior. Mapping data associated with the vehicle log is supplied as a collection of JSON messages. So we built a population generator that ingests JSON messages of this mapping data, populates a model of that mapping format, transforms those instances of mapping data into instances of the road subsystem in the vehicle guidance domain, and then emits the resulting population as Mika. So, JSON in one domain to Mika in another.
Leon Starr's vehicle guidance models originate in text form. Recall, he has an aversion to, as he puts it, pushing pixels around. But realizing that visualization is useful, he has developed a flatland tool which parses the text files, adds some positional information, and renders the models as PDF diagrams. At present, the flatland tool and the textual files it consumes are intended for one purpose only, to generate diagrams. You see, when John explained to me that Mazel, another xtUML dialect, originated in the United Kingdom, not only is supported by Bridgepoint, but also has a defined textual format, a way forward opened up. Enhancing the flatland parser offered a way to produce a complete Mazel representation of any flatland model, and thence, via Bridgepoint's Mazel import, a Bridgepoint representation. Adding an auxiliary parser that disassembles the one-line text description of each attribute presented by the flatland parser was relatively simple. In a strictly relational dialect as used in these models, there is no direct connection between a referential attribute and its corresponding identifying attribute. However, Mazel and Bridgepoint require that this connection be specified. Resolving a referential attribute to an identifying attribute in a referred to class when both attributes share the same name is trivial. Other cases may be less obvious. But for instance, if the target class of a referential attribute has only a single identifying attribute, And it's pretty safe to resolve that referential to that single identifying attribute, even if there is no name correspondence. However, when many classes have multiple identifiers consisting of various combinations of identifying attributes, the plot thickens somewhat. I developed several heuristic approaches. The one that came last was the realization that if a reflexive associative class has two unresolved referential attributes, they can both resolve to the single unmatched identifying attribute in the target class, but without any sense of direction. To achieve that, each side of the association must be allowed only one bite at the apple. Interested? Read the code. As it turned out, the augmented flatland tool did a pretty good job of resolving referentials and produced a report on those that may be suspect as a guide to manual editing before the Mazel to Bridgepoint import. While Mazel works reasonably well as an interchange medium between flatland and Bridgepoint, it does not support all of the xtUML concepts. For instance, it has no notion of subsystems and associations that span them. When textual xtUML is ready, it will replace Mazel in this flow. The original goal of the augmented parser was just to render the vehicle guidance models into Mazel so that they could be imported into Bridgepoint. At some point, it occurred to me that as the augmented flatland tool now had a good knowledge of the class and relationship structure, it would be pretty straightforward to generate the body of a function which would iterate over the class extents and emit the population data in any desired format, in this case Mika. The body of that function would be transplanted into a utility function defined in the population generator model we were constructing.
As I mentioned earlier, mapping data for the roads on which the vehicle operates is supplied to us as a collection of JSON messages. We built a model of this mapping format. Before this JSON mapping data can be transformed into instances of the road subsystem of the vehicle guidance model, it must first find its way into instances of that mapping format, that model that we built. We populate the mapping model with a small body of handwritten Java. It uses a JSON library to parse those JSON messages, and then it leverages the Sierra-generated API for the Java classes produced from the mapping model. So this little body of code creates instances of these Java classes and relates those instances together. Having a JSON domain or an external entity would have made this task much simpler and cleaner. Given an instance population containing mapping information, we can execute model-to-model transformations to produce instances of the road subsystem in the vehicle guidance domain. We do this with a collection of functions expressed in OAL. The population generator, the models of the mapping format, together with the road subsystem of the vehicle guidance domain, are compiled by the Sierra-Mellor compiler into Java classes. The generated Java is combined with the handwritten body of Java mentioned earlier, and then compiled into a population generator capable of adjusting JSON mapping data and emitting an instance population rendered in Mika. Given a pile of mapping data associated with vehicle log, the resulting program generates an instance population that is incorporated into a vehicle guidance program configured with the mapping data of interest.
Now to put it all together, we have an instance population for our road subsystem, but we need the class definitions. And to demonstrate, as proof of concept, a simple vehicle lane change, we need the vehicle dynamics subsystem, which contains the vehicle class and some dynamic classes representing maneuver life cycles. As it happens, some unconditional associations dragged another couple of subsystems into the mix. Our client had hand-translated these subsystems into Mika, providing state models for their dynamics and surfacing domain operations to support a stimulus interface. As Mika does not support the concept of subsystems, this would require manual concatenation of the files to produce a complete Mika domain definition. recognized that the impetus for automating the generation of the road subsystem population was the sheer size of the task if done by hand. For example, a small subset of the road subsystem corresponding to just 5 road segments generated 450 lines of Mica. It turns out, however, that hand translation allows for some flexibility of judgment. In naming classes, for instance, do we use key letters or the class name? Well, it may depend on the length of the class name. So, when it came to integrating hand-translated code with generated code, we came across some differences of opinion on such things as key letters, attributes, names, and such. The solution? Teach the Flatland tool to generate the class definitions for the road subsystem. Now they exactly match the population. And there we were. The Mica translator swallowed the assembled domain definition and the aggregate population files to generate a C program, which executed. A tickle script invoking domain operations to trigger a lane change based on recorded vehicle log data rewarded us with a pretty sequence diagram.
For more information on the open source bits of this project, please visit these links. And as always, if you have questions, feel free to contact us.